Okay, now that we're talking about pH, it's important for us to recognize that the nature of the acid itself alone does not dictate what the pH of the solution is going to be. There's two factors. There's the concentration of the acid, and then there's the strength of the acid. Okay, so we've said this in previous chapters, but we have acids that we consider to be strong and acids that we consider to be weak. Okay, and there's a fundamental difference between the two. But before we get into that, let's just list off these acids, because you need to be able to identify these on your own, and it's not that hard because there's only 6 strong acids that we deal with in this course. So we have HCl, HBr, and HI. Okay, notice the chloride, bromide, and iodide are all in group 17. Also, notice that there is no fluoride. Okay, that's not to say that hydrogen fluoride is not a nasty acid, but it's just not considered strong. Okay, then we also have nitric acid. We have perchloric acid. And then we have sulfuric acid. Okay, notice that sulfuric acid is different from all the others because it has 2 protons. And it turns out that the first proton is strong, but the second one that comes off is not strong. We'll talk more about that later on. And the weak acids are, well, every other acid. So it's fairly simple to remember this. Now remember, the difference between strong and weak was the degree to which the acid would dissociate in water. So in the case of a strong acid, okay, when we add it to water, we said that 100% of that acid would be converted to hydronium. Whereas for a weak acid, only a small percent would. Okay, in fact, we would have an equilibrium. Okay, we can make the same distinctions for strong bases. Okay, in a strong base, we're going to have a metal hydroxide. Okay, the metal could be any number of things. It could be calcium, it could be lithium, so group 1 or group 2. Any of those would be considered strong bases. But we can also have weak bases. Okay, and this is going to be anything that has a lone pair of electrons. Okay, and some bases are weaker than others. But notice that if I take a metal hydroxide and I put it in water, it's going to completely dissociate into the metal plus the hydroxide. Okay, however, if I take, I should probably show this, well, no, that's fine. If I take a weak base, though, and I add that to water, okay, we'll have an equilibrium. Okay, where the H will be attached to the weak base and will produce a little bit of hydroxide in solution. Okay, and again, notice that that is an equilibrium. So the big difference between strong and weak is going to be the fact that a weak base or a weak acid is only going to have a partial dissociation taking place. Okay, which means that it's going to produce much less hydroxide or hydronium in solution. Okay, so weak acids and weak bases are going to have a smaller impact on the overall pH of a system than a strong acid or a strong base. Now let's take this one step further and look at the anomaly that is sulfuric acid. Okay, so if I draw a Lewis structure for sulfuric acid, it looks like this. Okay, and you can see here that there are two acidic protons on here. Okay, we'll call it proton 1 and proton 2. It doesn't matter which one we call 1 and 2. In fact, they're indistinguishable from one another. Okay, but if I add this to water, there's going to be two processes that happen. The first one's going to be irreversible. Okay, this is going to be the loss of one proton completely. Okay, so we wind up with a negative charge here. Okay, plus hydronium is formed. Okay, so we're left with H2. And we can make a whole bunch of arguments for why that first proton should come off so easily. The second one, though, it takes a little bit more work. Okay, and that's because the molecule, when it's losing its second proton, already has a negative charge on it. And like we said earlier on, having a negative charge or building up charge is something that's generally not very favorable. Okay, so what that means for us is that, okay, it was easy to take that first one off, but the second one is going to be a little bit more difficult. Now, it still happens, but to a lesser extent, and it's an equilibrium process. Okay, so we make this as our byproduct plus another molecule of hydronium. Okay, so the first proton comes off easy, the second one not so much.